Hyman Rickover led the development of the very first nuclear-powered submarine. He said that automation makes people stupid. Look at how upset he looks here. It's not the 50s anymore. Automation is not just a good thing, but it's actually urgently needed. Registration can be further improved using machine learning, aligning point clouds with one another. I'm really hopeful for eventually cracking this.
How are we doing? We're almost there, guys.
So about 10 years ago, I was working as a junior project coordinator on a large nuclear power plant refurbishment project in Ontario, Canada, where I'm from. And I was invited to watch a documentary about this man, Hyman Rickover. Who knows this man? Anyone? So Hyman Rickover led the development and construction of the very first nuclear-powered submarine. Turns out, Idaho actually was kind of central in the history of nuclear power. There was a nuclear reactor testing station in Arco, just a 3-hour drive east of here. And this is where they built some very important early prototypes of nuclear power plants, as well as the reactors that went onto the vessels. So imagine this, 1945, we have Trinity. 1951, we have the first nuclear power plant. And then in 54, just 9 years after Trinity, they put into service the USS Nautilus. This was the first ever nuclear-powered submarine. So in a span of 9 years, we invented nuclear engineering, we developed the entire nuclear supply chain, we designed the first nuclear power plant, built it, designed the first nuclear submarine, built it, and put it into service. 9 years. It's kind of crazy to think, like with all the big infrastructure projects kind of taking forever these days. And it's made all the more incomprehensible by the fact that the nuclear navy has like a really good safety record. I think they've traveled like 250 million kilometers using these things and haven't experienced a single radiological incident. So Hyman Rickover was extremely anti-automation. Like, he hated automation. He fought tooth and nail to keep automation out of all of his designs, and he was involved in the designs of both the power plants as well as the submarines. He thought that if one of the crew members wanted to turn on a pump, they would have to go to the pump and turn it on manually, so that if something was wrong with it, like if it was leaking or smoking or grinding its bearings, they would see that and they'd be able to fix it. He said that automation makes people lazy and stupid. Like, look at how upset he looks here. Thinking about Hyman Rickover and the great success that he had with the development of these super innovative technologies, it makes me wonder, like, is automation a good thing or a bad thing? Like, I'm an applied machine learning scientist. I live and breathe automation. I'll argue that automation is not just a good thing, but it's actually urgently needed. Because it's not the 50s anymore. Builders today have to contend with a mountain of considerations beyond just the technical. In my city of Toronto, we have a major traffic problem. We've been trying to deal with it forever. Like in 1986, this was the first mention of a new subway that would cross Eglinton Avenue. We are only now just putting that subway into service. So it took the city 40 years to wade through all of the assessments and interest groups and litigations and regulations and bureaucratic fragmentation and funding issues. It's hard not to hear stories like this and think that we have somehow paralyzed ourselves with red tape. And it's because of this red tape that on another project in Toronto, this is the new Ontario line, we have collected 15 terabytes of reality capture data. And this is reality capture data of all kinds, and it's used to answer this red tape conundrum, like all the studies, all of the assessments, all of the public hearings, the visualizations for those things. We are essentially drowning ourselves in information in an effort to answer this red tape. And it's only going to get worse, like with the sensors getting cheaper, with storage getting cheaper, connectivity becoming cheaper. We're only going to generate more information. And if history is any guide, that red tape is also going to continue to increase. With all the problems in the world, I don't know whether we can get out of this without automation. Like, we need to be faster. We need to be more agile. One final kind of anecdote, and then I'll get into the machine learning. So, information technology, including automation, like structures and reforms the physical environment in very tangible ways. If we consider tall buildings for a moment, what makes tall buildings viable? Yes, it's the steel. Yes, it's also the elevator. But just consider for a moment whether tall buildings would be possible without the telephone. The telephone is not just a communication device. It has changed the way that buildings are used. It is the thing that allows so many people to cram into a single tall space. Like, try to imagine all of the people, all of the messengers that would be required if we didn't have the telephone, cramming themselves into stairwells, into elevators, walking through lobbies, navigating offices. It would be total chaos. Tall buildings would not be viable without this information technology. My contention is this. In the same way that telephones make something like a tall building possible, that automated processing of reality capture data is going to make buildings, as well as the rest of the built environment, more agile, and that's something we desperately need. The floor area of a building is an important quantity. The company that I work for, Integrated Projects, measures the floor area for every single project that we receive. So we do scan to BIM. The first step of that is we receive point clouds from customers. We verify what the floor area is so that we can price the project. We're doing close to 6 projects a day right now. So we are really interested in automating floor area verification if we can. Instead of opening a point cloud and manually tracing out every floor area of every level of a building, can we maybe automate this without any kind of manual human intervention involved? Over the next 20 minutes, I'm going to take you through a kind of a speed run of the development of this floor area estimator system. And I'll talk about the things that we learned, the challenges that we faced, and where this is all going for us in the future. The first step in any machine learning initiative is understanding what is possible with the technology. I'll be honest, there's kind of a tendency to overhype the tech. And I'm not here telling you that machine learning is the secret that is going to solve all of your problems, because there are cases, many cases, where human expertise is absolutely still essential, where traditional software is still the best option. So what should you consider automating with machine learning? There are a few criteria that I use. First and foremost, any task that is repetitive is a good candidate for automation. Because machine learning can be unreliable, If the errors are low cost, that's also a good thing. Like, you don't want to be the self-driving car company where an error is fatal. If you want the process to also be performed at a really large scale, and maybe labor is cost prohibitive, that's another good sign. And finally, if the patterns in the data are complex when going through the task, that's also a good thing because machine learning is good at complex patterns. So where do you start once you've identified a task that is a good candidate for automation? I'll say right now that if you're creating machine learning stuff from scratch, you're putting yourself in danger. Like, you want to be using stuff that is already existing and proven, and you can just take the architecture off of the shelf. There are tons of existing architectures that do all kinds of things. Semantic segmentation is probably the one that everyone here knows about. You give it a point cloud, it spits out all of these objects isolated as well as classified, so it'll tell you what a chair is, a table, a window, a wall, that kind of thing. You can use this semantic segmentation for all kinds of practical tasks, like you can do defect detection, change detection, modeling. But there are architectures for doing a lot of very important and kind of niche things, like registration can be further improved using machine learning, aligning point clouds with one another, even if the environment is changing. One of my favorites that I don't hear talked about very often is that point cloud completion, where you can take a scanner through a space, not really care a whole lot about occlusion, and neural networks, based on their understanding of the world, will fill in the gaps. At a high level, machine learning is an approach to learn complex patterns from an existing data set and use these patterns to make predictions on new data. The major breakthrough of machine learning is that we can, rather than telling the algorithm what patterns it should rely on in order to make these kinds of predictions and decisions, it actually learns what patterns to rely on from a data set of examples. This is your training data. There are many approaches to training data. The one that is most commonly used in academia is something called hand labeling. During my PhD, I spent months of my life labeling thousands of images like this. It is kind of the gold standard of quality, I guess. You do it with the one purpose in mind of using it to train a neural network. There are tons of platforms available to do this kind of hand labeling. There are companies out there that are more than happy to take your money to do it for you. It is expensive, and it takes a very long time. I would strongly advise you against approaching machine learning in this way. For many reasons, but the main reason is that if you are hand labeling data, that is a pretty good sign that you are trying to automate a task that is outside of your business's core competency, and you are probably going off the rails strategically. I would suggest, rather than doing hand labeling, you look for tasks where your business has what I call inherent or natural labels. These are labels of data that your business creates as a natural byproduct of standard business process. For integrated projects, the training data for floor area estimation falls into that category of inherent labeled data because we deliver a standard business process models to our customers. And so we have labels for virtually all components within buildings, floor slabs included. The question everyone asks me when it comes to data is like, how much is good enough to get started? And I'm going to give you an unsatisfying answer. It really depends on the domain in which you are trying to automate the task. Like, how much variability is there? How diverse is the data that you are trying to process? If the domain that you're operating in has a lot of data diversity and the task is looking at patterns and objects that have a lot of variability, you're probably going to have to create a really large data set in order to cover all of the edge cases. But if you're operating in a domain where everything is kind of similar to everything else, there's very low variability, very low diversity, you can probably get by with a very small data set. But I'll also warn you that the world is changing, data sets change, collection hardware changes, and if you use a very small data set to train a neural network, it will probably be very fragile to that change. So you've got some tasks you think you might be able to automate. You've looked through Hugging Face and GitHub, and you found maybe a few out-of-the-box architectures that might be able to serve you in automating this task. What now? I think leadership needs to start considering automation to be a kind of a strategic priority for the company. Because if it doesn't, it's going to make hiring very difficult. The moment when you hire, it really comes down to when you find the right people. Because the people, in order to do this kind of automation, are kind of rare. Like, they have to have like 1 million different skills, be super interdisciplinary. That's why if you find someone like this, it's probably a sign to give automation a try. I joined Integrated Projects because they pitched me a vision where automation was like a core strategic priority for them, where it was going to develop into a competitive advantage that they would take into the future. They also showed me their data set. They said, listen, we have the largest scan-to-BIM data set in the world. That was super compelling. Not only is it large, but it's also incredibly diverse. Because we accept point clouds from virtually anyone using any kind of kit, scanning any kind of facility, it lends itself well to creating machine learning systems that are incredibly robust. Not only that, but early on in the company's history, the founding team decided that they're not going to negotiate with customers about what is going to be modeled and how it's going to be modeled. Usually, scan-to-BIM service providers will sit down with a client. They'll say, okay, what LOD do you want? What do you want modeled? What don't you want modeled? We said that just takes too much time. If we want to operate at a really massive scale, we need to just bring together some experts, set a standard operating procedure, and say, take it or leave it. The customers that accept the standard product get something that is low cost and delivered quickly. The ones that need something more go to the specialists. The reason this is important for automation is that because the data set is so standardized, it is extremely easy to exploit for automation. Like, when I'm in the office writing scripts to move data around, to reformat it, to prepare it to be shown to the neural network, variability in things like naming and contents is my enemy. And the fact that they decided to just deliver a standard model in all cases has helped me a lot. Early on, I was speaking to the founder, Jose, about how we should form this initial kind of small starting team. There are essentially two functions that need to be filled. There's the scientist, and then there's the engineer. The scientist is the one that kind of prototypes, invents the system that does the task that you need done. And then the engineer takes the prototype system and packages it into a production pipeline that you then deploy to an application or to the cloud. These are the skills that we look for. As I said, it's hard to find someone that has all of these skills. You're probably going to have to go digging in PhD labs at the top universities, but they are there. They're also going to be, talking with big tech, so you're going to have a very compelling story about how you are, I don't know, saving the world or something. I would say you're probably not going to find the perfect candidate. The one thing that I would say is non-negotiable is that they have the courage to give this task like 100%, because that is the thing that is going to make this whole thing work. The first thing we did was draft the automation roadmap. This is where you kind of strike the balance between like a million things. I would say that the roadmap is where you kind of set milestones. Floor area estimation is not the end goal. It's just kind of like the very first trial run, just so that the team can prove their competence. The North Star of automation in this case is automation of scan to BIM. Where the conversation kind of started was we're going to automate a process in order to facilitate our usual scan to BIM pipeline, just verifying floor areas. One risk when road mapping is that this early focus very quickly devolves into a conversation that leads in a million directions. I'll give you one example. So in our enthusiasm, we started to imagine what a derivative product might look like. We said, well, there are these things called building measurement services that deliver reports that, have all kinds of different areas. And we started to look through our data set to figure out, could we actually deliver a report that is fully automated, that conforms to these usual kind of real estate standards, reconfiguring the data. We said, well, we can probably get things like boundary areas, but classification of space as well as wall priority might give us a problem. Well, how do we deliver this? Maybe we can reconfigure the elements within our models, relying on maybe ceiling elements, feeding in elements from the spaces to a large language model to try to figure out what the space is being used for. And that is exactly the kind of behavior that leads to stagnation and ultimately failure. Because AI is so hot right now, there are like a million things that you can do. And here, people are just like, oh my God, there's the opportunity to generate this whole new revenue stream. Months of delays. This is probably the hardest part of my job right now. How do you stay focused on something that is practical and solvable? So after a reasonable roadmap is put together, you start to design the system. These are a few of the guiding principles that I would give to you when creating this design. You want to start with the simplest possible version. Don't overcomplicate things early on. You want to use off-the-shelf technology whenever you can, and there is a ton of off-the-shelf stuff. You don't have to be building things from scratch. Leave that to the academics. You want to use mature technology when possible. I know the state-of-the-art stuff looks really good. You read some paper somewhere, some article that says you can get some crazy high, accuracy or precision or whatever. It's all smoke and mirrors. They probably tweaked the hell out of that thing in order to make it perform really well on a very small test case. Use the stuff that's been around for 5 years, 10 years. That's the stuff, if it's still around, has proven to be reliable. And finally, you also want to be mindful of licenses. Just because it's on GitHub doesn't mean that the creator has given their permission for commercial use. When we were designing the floor area estimator, we had to make a decision. Do we frame this task as an image processing task? Or do we frame this task as a point cloud processing task? We did some tests, and when we had to make the final decision to move ahead, we decided to go with the more mature technology, that is the image processing. I'll talk about some challenges that we experienced during development. So when we first started to generate these images, again, we were framing this as an image processing task, we discovered that it was going to take a very long time to generate this data set, which ultimately would be on the order of 1 million images. So, as you have to, you optimize your code, and this allowed us to iterate a lot faster. Another problem that we encountered was when we were generating the pairs of data. So a data set is you have an input to the neural network, you have an output that you expect the neural network to give you in return. Here, the input was the point cloud, the output was this floor slab representation. And we were generating these pairs, and we discovered that the model and the point cloud weren't aligning. Like, what the hell, right? This was an existential threat to our automation initiative. If we couldn't figure this out, the data set was essentially useless. So thankfully, we found a way to extract transformation information out of thousands of Revit files using some custom tooling. And so we managed to recover from this one, but man, I lost some sleep here. Another problem is something called imbalanced data. So one of the main distinctions that a floor area estimating system needs to make is the distinction between interior floor space and exterior. Our data set is 90% plus interior space. And because exterior space is so underrepresented within our data set, it's hard for the neural network not to ignore it entirely. And so in the case like this, where there is such a large difference between these kinds of categories, you have to do some class balancing. So I hope these examples kind of give you a sense that data is everything, but data is also the hardest part of machine learning. Like the neural network stuff, that's easy. You can learn that stuff in a week. It's the data that is going to give you the most trouble. Even in the case of integrated projects where we have this immaculate data set, we were still experiencing issues that were like existential threats to the whole program. Another tension that you will constantly be experiencing is, do we continue to iterate and improve the systems that we've already developed, or do we move on to new things? In the case of one of our earlier neural networks, the floor area estimation was giving us this super noisy boundary. In this case, we decided to spend the time to improve the results. The way we did this was we introduced into the training data a totally separate boundary class that forced the neural network to pay particular attention to that boundary. With machine learning, there are no guarantees. It's not going to be perfect, and when you're reporting performance, when you're studying performance, I'm really not a big fan of summary metrics. Like, you can run a test case through a neural network and get something like 95% accurate. You're not going to learn anything by evaluating and studying those summary metrics, because what the heck does 95% accurate even mean? You're going to have to create tooling to kind of peer into what is going on inside of the neural network. In the case of floor area estimator, we would be kicking out these visualizations so that you can actually look at what the neural network is categorizing as floor area and where it is failing. Like, what are the failure cases? What is the context in which it is failing? And it is through this kind of deep study that you understand where the data set is lacking. Here, we see floor area estimator failing on an indoor basketball court, which tells me that maybe there aren't enough indoor basketball courts in our training data. This can be overcome using a number of methods, but now I'm aware of the problem. This is also something that we kick out for every project that is processed by floor area estimator, so the people that are relying on it can see and quickly verify, like, did it work? Did it fail? Why did it fail? So we finished development of floor area estimator, and it's working quite well. we package it in a production pipeline, we deploy it. And in come the flood of emails complaining about how shit it is. Like, it's giving us floor area estimates that are all over the place. In some cases, it's many multiples off the real value. I'm like, fuck, why? It was working on my computer. So I look into the visualization, and this is what I see. And I'm thinking, whoa, that looks very different than what I was seeing on my computer. Kind of doing the investigation, I noticed that the input images, the projection of the point cloud, was exhibiting these kind of horizontal and vertical black lines. And this is not something that I saw during development. I started to think, like, what could be causing this? And I thought maybe there's some kind of interference between the way I'm projecting and maybe the way the point cloud is being subsampled. That ended up being a dead end. Then I found it after some, searching. Turns out when we were optimizing the code for production to save cost on compute, we were loading the point cloud in using a half precision variable instead of single precision. It's kind of a nuanced point, but it just shows you how fragile these systems are. We loaded them in using full precision, and the problem was solved. This kind of difference between the data that the neural network is trained on and the data that is processed through the neural network during production, any difference between that is going to be a constant challenge. In this case, the difference was introduced using this optimization of our production pipeline, but change is constant, and it's going to come from everywhere. Like, LiDAR hardware is changing, the way we process laser scan data is changing, and every time something changes like that, the neural network is going to have to be updated. All right, so floor area estimation is in production now. It supports pretty much all of our projects. It is saving probably like an hour or two of time on every project that we receive. So what next? Now we kind of take everything that we learned on floor area estimation, all of the infrastructure that we developed for floor area estimation, and we move on to the next thing in the roadmap. BIMit is our scan-to-BIM service. We take as input a point cloud from customers, we convert it into a Revit model, and we deliver it. It's essentially the same process as floor area estimation. You take as input a point cloud, you recognize an element, and you input it into Revit. This is a test that we ran this spring. It's kind of a side-by-side of manual modeling of our architectural scope and what our automation system is capable of. We've gotten permission to show it. So we're making progress pretty quickly. One thing that I have as a guiding philosophy and something that was shown in a very famous essay that came out in 2019, it's called The Bitter Lesson of AI. The bitter lesson of AI is that whenever human researchers try to be clever, we tend to mess things up. And instead, we need to kind of get out of the way of compute and data. Using super flexible systems, large data sets, and a lot of compute is usually the way to go. And if you can find a way to align yourself with that philosophy, development tends to be very fast. And so we've done half of architectural scope so far. We're releasing new elements internally pretty much every other week. And I'm really hopeful for eventually cracking this. If you want to talk about AI, about ML, about scan-to-BIM, please add me on LinkedIn, reach out. I'm always happy to talk about those topics. That's all I got. Thanks, guys.